My name is Tim Rugh, Executive Director of 3A Sanitary Standards, Inc. On behalf of our leadership, our education committee, and our faculty, I want to welcome you to our webinar series. These webinars were originally presented as part of our 2022 education program designed to clean, creating a hygiene-focused culture. We welcome you today to join a truly diverse group from across the United States and around the world who share a common interest in hygienic equipment design. Our participants include those who fabricate the equipment, those who use it, and those who are responsible for inspecting equipment and facilities. We especially welcome those who are participating for the first time in a 3A SSI event. Let me also recognize and thank the sponsors of 3A SSI. These companies have stepped up to show their support for the education mission of 3A SSI with a sponsored link on our website. Their support helps make this webinar possible, along with many other vital education resources. Follow the company link on our website and visit these companies for more about their hygienic products and services. Since many participants joining us today are new to 3A SSI, let me share a very brief history about the organization. In the 1920s, 2 trade associations and 1 professional association formulated uniform standards for fittings used on milk pipelines. The standards became popularly known as 3A for the 3 associations. This cooperation between industry and regulatory experts continued over the decades, and in 1944, the U.S. Public Health Service, which oversees the FDA, announced it would collaborate in developing uniform equipment standards. In 1956, the 3A symbol was introduced as a legal trademark for display on equipment that conforms to a 3A standard and other conditions of licensing. Through many decades, the number of 3A standards and accepted practices increased in number and in complexity. Today, we oversee an inventory of about 80 standards for equipment and accepted practices for processing systems. In 2002, this network of informal collaboration became organized in a modern, not-for-profit 501c3 corporation. We are headquartered in McLean, Virginia, just outside of Washington, D.C. This is probably one of the most important slides you'll see today because it conveys the long history of 3A and the important role it serves in supporting regulatory programs in the dairy industry. Now, as we head into the 2020s, 3A is entering the 2nd century of service to the food processing industry. That's a long and rich history. Today, 3A SSI has 3 member associations that represent the same stakeholder groups of years past: fabricators, processors, and regulatory sanitarians. The Food Processing Suppliers Association is the trade association for suppliers to the food processing and packaging industry, with more than 400 members serving a broad spectrum of industries, including bakery, beverage, dairy, meat, pet food, and prepared foods. The International Dairy Foods Association represents the nation's dairy manufacturing and marketing industry, with a diverse membership ranging from multinational organizations to single plant companies, from dairy companies and cooperatives to food retailers and suppliers. IEFP is a member-based association of more than 4,500 food safety professionals committed to advancing food safety worldwide by providing food safety professionals with a forum to exchange information on protecting the food supply. The 3A SSI Board of Directors is composed of voting representatives from these associations, plus representatives of USDA and FDA, and the chair of the 3A Steering Committee. This is the committee responsible for overseeing all 3A standards activities. All of the corporate activities are now carried out by a single organization with its own governance structure and a dedicated professional staff. The support for 3A SSI operations comes mainly from the licensing program, sales of documents, meetings, and dues. 3A SSI today has vastly expanded and modernized its programs and resources dedicated to hygienic design, particularly in the past 2 decades. One of the driving forces for the new 3A SSI was to improve the integrity of the 3A symbol program used to identify equipment that conforms to a 3A sanitary standard. As we look to the future, I'm reminded of a widely known and well-regarded speaker who said something to the effect of, "Standards are good, but you don't need 3A. Sounds a little dismissive, but it's probably true. To be fair, there are many other voluntary guidelines and standards available, also very good, but you may not need them either. It's up to you to learn about what you do need. It all begins with sound education. It's worth pointing out that 3A is not strictly US, nor is it exclusively dairy. We note that of the 3A symbol authorizations on file with us, about 48% are held by US entities and 52% are held by international entities. The 3A symbol authorizations and certificates held by companies span about 22 countries outside the United States. We also see that 3A SSI document sales reach a very diverse group of customers in 40 countries outside the United States. And these are companies that are certainly outside of the dairy industry, including beverages, pet foods, cereals, personal care products, wine, beer, and many other types of food applications. We also know that the key drivers for hygienic equipment design are US dairy regulations, the Food Modernization Act, and corporate requirements. Looking across the landscape of other standards developers, 3A SSI offers a highly respected network of subject experts in hygienic design and high-value education and training resources. Thank you for taking advantage of this education opportunity today. Before we begin, we urge you to explore the Knowledge Center and build these resources into your personal education or organization training programs. Here you'll find 4 basic e-learning modules on hygienic design and 1 advanced module, all at no charge. They're designed for all audiences, including equipment fabricators, food processors, regulatory sanitarians, as well as students and young professionals beginning their careers. No previous knowledge of hygienic design or a given topic is required. The 3A Sanitary Standard for General Requirements, or simply the General Requirements, is a compendium of terminology and requirements which are common to our standards and accepted practices. You may hear references to these requirements in today's webinar. This document is essential if you do plan to utilize 3A SSI resources for your future training and education. This document is available for purchase from 3A SSI through the link on our homepage. Don't forget to mark your calendar to join us for in-person education and networking next May in Bloomington, Minnesota. We'll have 2 days of education beginning with a special introduction to the foundations of hygienic design, followed by a day of special topics. We'll also conduct our annual meeting and work group meetings. Watch our website for the program schedule and details later this year. So let's begin today's presentations. Remember, the presentations you are viewing today are not live, but we still invite your questions or comments on the content. Please use the email you received with the access code for this program to submit your questions. We'll provide a response to your question from the presenter. You can also contact any 3A SSI staff member about other subjects. Now let us begin today's webinar.
Welcome, everyone. And what we're going to do here is share in this conversation about plant environmental air practices. We've got a short intro. We're going to talk about why we're here, what you should get out of this. We've got some factory level considerations, some best practices. Roger's going to go into some air system engineering. And then we hope to address some of the top issues and questions. I've spent most or all of my career, except for the last 6 months, at General Mills. A lot of that was designing, engineering, installing, starting up, and maintaining, large-scale food systems across General Mills and all of their enterprises. And I did spend time in manufacturing, some time in quality control, retail operations, but a lot of heart still in the sanitation by design.
Again, my name is Roger Porter. I've been doing HVAC engineering for about a little more than 25 years, all at one firm. I got a mechanical engineering degree from UW-Madison, and Most of my experience is in dairy, but I have done a lot of other work in bakery, confections, meat, and other things. So I've got a pretty broad background in all of that. So, and I'm also licensed in a bunch of states as a professional engineer as well. So.
Okay, so why are we here? To give you some insight as to the best current practices and emerging trends in building and HVAC designs as they relate to the 3A standard 612, accepted practice for plant environmental air quality. So why is the plant air quality important? I'd like to kind of just talk about two things. It's about people and the process. Certainly the people, you're protecting their wellness when they're in your manufacturing organization. OSHA has rules also about how you protect people and limiting their exposure to safety risks. Another thing is trying to keep people in the building. You want them to come back the next day. And sometimes that means you have to make them comfortable and know that they're being protected in what they're doing. Another area, of course, is really that a lot of process and packaging systems are dependent on the air quality. Dr. Warren was talking about the ready-to-eat qualifications and things like that. And after 30 years in food, I think that ready-to-eat is really in the eyes of the beholder. There's a lot of pizza that's frozen that's not getting, not going through the oven, okay? People are eating it, and just think about what that means. How do you protect for when people skip that kill step that you're depending on? Or even, and I've never done this, but maybe brownie mix. Maybe people think it's good on ice cream or something, and that's not ever going to get baked up. So they had flour up there, and that's certainly been a big area of interest because a lot of things are getting consumed without getting baked, without that kill step. So also, really, there's been a lot of optimization of production, and your air systems are a big part of that. Everybody's pushing for more, faster, more turnovers, quicker downtimes, getting back into production. And then they're having to pay for it. So sometimes, we've been looking at these massive projects, and then you sit back and go, are we trying to build a soup manufacturing system, or are we building an air quality system here? Because the costs are staggering. And you can't just demand, oh, I need all this, without understanding really what those costs are going to be. Not only does it cost a lot up front, but then depending on what you're building there, you may have a lot of operational and maintenance costs to support that system. Then also there's food and regulatory, food safety and quality things that you have to maintain. And lastly, I think protection of your assets. So making sure that the air is also not damaging your equipment or making it, shortening the life of that. Okay, so Roger and I have kind of broken this into three primary steps to safeguarding your plant environmental air quality. First is really the site level design and management. Second is an integrated zoning plan and understanding your manufacturing flow. And then last, Roger's going to talk about engineered systems to deliver those air quality requirements. So first, it's really about the site and the grounds, where you are, who your neighbors are, what happens during the year when you're there, what can you expect to be trying to penetrate your plant and ruin a good thing. So assessing and identifying those risks and understanding what the required controls are going to be, securing the grounds in the building, pests, moisture, other contaminants, and then really the traffic flow. How does everything get around? How are you going to get your people in and out? How are you going to get materials, utilities, all these things, and how are you going to grow? If you've got big plans, everybody's going to grow. So are you boxing yourself in a way that's going to be compromising your risk later on? Some important considerations. Dr. Dave over here talked about the drying up your factory as a large part of the pathogen management. I can remember 25 years ago, our quality group said, we're going to wet wash everything. Cereal, low moisture, areas where, it's a little bit wet, but we didn't ever turn a hose on it. Well, then you start doing that, and it was great because, again, you could change over from one product to another, get into business, reduce those downtimes is free production. So a lot of pressure to do that, and wet wash was an answer for a while, but then all the microbes started appearing, and that became a deadly sin if it was managed badly. So most of those buildings, if you're in a building that's more than 25 years old, it's probably not built to have wet washing areas that you may be wanting to wet wash. So you got to be very careful about that. But in general, after that happened, it's been, everybody's got their version of war on water, and where you got to use it, you got to use it, but where you don't, or you may not, you really want to eliminate it. Another big consideration is that humidity control is a big factor in drying up your plants, but that can get very expensive. And I wanted to make a point that you should understand the minimum requirements. So a lot of times 50% RH is kind of a barrier where you want to hit for a lot of different reasons. But some people think, well, if 50% is good, maybe 20% is better. Well, 20% may cost you 3 times more to get to that when you don't really need it. So be careful because, again, the economics are going to be substantial when you're dealing with that kind of thing. And then if you are going to be using a lot of humidity control and refrigeration becomes an important thing. Are you into Freon, ammonia? These are important considerations. Some of these things are being restricted as you go forward here. Talking about the integrated zoning plan and manufacturing flow. Now, really understanding your boundaries. This diagram here is right out of 3A module number 3. Where are your raw materials, your raw processing happening? Where's the finished product, the storage, utility waste, employee welfare, all these things. You should really think about it. Like if you look at this chart here, okay, if I've got ingredients on one side and I got to take, and unbox and unwrap those ingredients, and I got to take that garbage. Is the only way to get it to the dumpster by going through the packaging room or the process room? These are things that are going to really, upend your plan for controls. There's also special things to consider. Are there rigid temperature and humidity controls that are important? It's great to put that cartoning system in the warehouse, but then for some reason, I can't run my cartoner at high speed because the cartons are all warped because of the humidity that they just drew in. So a lot of these things are going to be impacting, again, the opportunity to produce at the highest rates and to maintain control. Of course, then there's the super high risk areas, culture room, the fillers. People have been talking about that, and how do you manage that? It's I think in our world of learning, the bigger the space, the harder it is to get the controls you want. You're better off in a big space trying to get an envelope of control that's very isolated so that you don't have to worry about that because you can't keep everything as clean as you want it. And then isolating hazardous areas. There's always construction and always modifications happening. How do you manage those upset conditions when you're being asked to maintain production, even though you're doing some pretty hazardous things right next door, dealing with those temporary situations. So one thing that has become an important tool is really this thing we call in the engineering process called the room design criteria. And it's taking every area that you're going to be working in and identifying a hygienic zoning plan for that room, that space. The biggest question is it wet or dry? So how am I going to be keeping that room dry, or do I need to have it wet? What is the equipment and the materials that are going to be in there? What are their needs? Do they have wet utilities? Do they have steam and condensate? Do they have other needs that are going to be impacting how I control that zone? What's the manufacturing cycle look like? Is it all 70 degrees all the time, or do I have to shut everything down And when I'm cleaning, it's a steam room basically for about 6 hours, and then I got to get back in production. You know, what happens in the middle of summer when it's 104 degrees outside, and I got to keep 40 degrees in this area, and my engine room is strained. What are all those peak conditions, and how do I get through those peak demand times? You know, who's in there for how long? What methods are they going to use to clean? What are the traffic flows? Who's dragging what through there? And then what do I need my air to do? And then there's other, you know, things, dust, gases that may bring aromas and things like that in there, or allergens. So really the job the air has in a space is determined by that room design criteria. The air system supports and or maintains control of those things on the left. Usually temperature, humidity are the number one and number two, and then the space pressure. If you're in a sensitive area, you always want to have slightly elevated pressure so that when a door's open or when there's a penetration in the wall somewhere, that the air from that room is going to go into a room that's less sensitive for that. Okay, I'm going to hand it over to Roger now for the engineering side.
Thanks, Tom. Well, so far Tom's given you a pretty good high-level overview of the kind of the building and some of the concerns we have about isolating different areas and trying to ensure good air quality in the building. So I'm going to dive a little deeper into air handling and HVAC systems and how we look at those and how we go about addressing air quality in a plant. So, you know, as a design engineer, we've got to consider a lot of things when we're designing a food-grade air handler system. And I'm not going to go into a lot of detail about all of these, but, you know, the functionality of the unit, how easy is it to clean, how long is it going to last? You know, the food plant air handling units should last a lot longer than a commercial grade air handling unit. If you put that in a food plant, it's going to last about 5 to 10 years max and then wear out and fall apart. So that definitely has to be considered. Safety, always important with food plant air handlers. A lot of times you're dealing with higher pressures and temperatures, and there are some more inherent risks with food grade air handlers, so those have to be addressed. Affordability, food plant air handlers are expensive. They're not cheap. You know, a good size air handler can easily cost $250,000 or more. So, and maintenance, you know, downtime's critical in a food plant. These units have to be easy to maintain and fix. So all those things have to be considered. You also have to consider the flexibility of the unit, how it operates. If you need to make changes on the fly, how easily can you do that? Controls are important in an air handler. Are you going to connect it to the plant PLC system or not? Or is it just going to be standalone wall panel in the process room? What kind of precision are you looking for with this kind of HVAC unit? Do you want plus or minus a half a degree Fahrenheit and, you know, plus or minus 2 degrees or 2% relative humidity? Obviously, you're going to pay a lot more for high precision. So that's another one of the factors that needs to be considered when you're designing HVAC systems in a food factory. Location, where are you going to put it? These units are very large. They're a lot bigger than a commercial grade air handler. So it's not uncommon for them to be upwards of 40 feet long, 12 feet wide, 10 feet high, and weigh 20, 30,000 pounds. So making sure you've got space to put these units in and to access them and get in them and clean them is important. Utilities, what's available? What are you going to use for heat? Steam, natural gas, hot water. What are you going to use for cooling? Ammonia, chilled water. Evaporative cooling, which generally in a food plant you don't want to do, but there's rare situations where it might make sense. And life cycle cost. You want to design these units to be as efficient as possible, because as much as they cost, as much as their first cost is, the amount of energy they consume is huge. So you really want to make sure you're not wasting energy. Just a little bit for those who may not be familiar with HVAC in general, I just wanted to spend a minute or two just kind of talking about HVAC systems and what they are. HVAC system, in its simplest sense, is two major components. One, there's the box, the HVAC unit, the air conditioning unit that treats the air the way you need it to be treated. It'll heat it, it'll cool it, it'll filter it, and it'll have all the controls associated with it to make the unit do what you want it to do. So. And you also have to consider, you know, like I said earlier, where are you going to put it? There's significant structural engineering implications about where you put these units. And that's the first part. The second part is the air distribution system. Once you condition the air, you treat it, you got to get it out to the spaces where it's needed, because you almost never put these large air handling units inside a process room. So usually they're in an interstitial space or on the roof or a mechanical room somewhere. So you got to get the air to the space. Well, how are you going to do that? Well, you're going to do that with ductwork typically. And that usually consists of supply duct, return duct, outside air duct, or also called makeup air, and then also exhaust air to get the air in and out of the building. One of the things that's important about the ductwork is its accessibility. You don't want to run ductwork through sealed off spaces you can't get to, because you need to be able to go in there and clean the ductwork out with access doors in the duct. So that's also an important consideration. And then diffusion points, the last system of the air distribution, the last component of the air distribution system is the terminations, the diffusion points, where you've got registers and grills and things that'll blow the air into the space. So that's at a high level, that's HVAC 101. As we kind of alluded to earlier, one of the critical things about HVAC systems, and one of their main purposes, is to dry the rooms out. Way back when I started engineering HVAC systems, it wasn't uncommon for me to see older plants that just had large makeup air units where they would bring a huge amount of air in, heat it, no cooling, and dump the air in the most critical process room, say a starter room or a vat room in, say, a cheese plant. And then you would just transfer the air to lesser critical rooms and then eventually exhaust it out of the building. So that was single pass air through the building and out. They just moved huge amounts of air, didn't really worry about humidity levels in the space, weren't worried about wet rooms, floors were always wet. It just didn't matter. Well, over time, as we've gotten a better understanding of bacteriology and how that stuff grows in food rooms, we've been working harder and harder over the last couple of decades to dry the rooms out. These air handlers are critical in doing that. So once you get into designing these systems, it's important for the HVAC engineer to talk to the client and get an understanding, either see a similar space to the one that's going to be designed or built, or if it's an existing facility that needs to be fixed in some way, get out there, look at it, have a conversation with the building owner, the plant manager, and all the people on staff that know how the building operates and the process operates, and go through where all these sources are. Do you have wet floors? Do you have pieces of process equipment that are chilled or cooled in some way that have wet surfaces where you've got condensation issues? Do you have heat exchangers in the room that either leak steam or hot water or sweat because they aren't insulated? So you got to go through all of these different things. There's other things like pump seals, dairy fillers, and other pieces of equipment that'll produce moisture in the room as well. So you got to identify all of those and then use that information to design the system to try to get rid of all of it. Typically, there's a lot of different ways you can design these air handlers to operate in a space, but the most common way I see it typically is to design these HVAC systems with primarily two operational modes, a production mode and a cleanup mode, where in production mode you're making food product and the unit just runs to heat, cool, filter air, just maintain the temperature, humidity set points you need in the space. Typically those units are sized based on all the loads in the room, the number of occupants in the room, the heat gain in the room from process equipment, motors, heat exchangers, the heat gain from lights, heat gain from building envelope, and a lot of other sources. Those all add to the heat gain or moisture gain in the room. So we've got to get rid of all that. Once those things are identified, an HVAC engineer can just do calculations, figure out how much a heat gain and moisture gain that is, and size a unit, and size the airflow for the unit to get rid of it. That will result in an air change rate for that room. And one point I wanted to bring up is when I first started the HVAC engineering, a lot of times I would just have a client or a peer just say, 20 air changes an hour is good for that room. We've kind of steered away from that. We don't do that as much anymore. We'll use it as a back check, but the two concept of doing precise load calculations to figure out how much air you need in a room and using a flat air change rate they don't typically align. You don't normally do an air change rate calculation. It just turns out to be 12 air changes an hour or 20. It's some value. If you just size for a flat air change rate, you could end up significantly oversizing the system and making it way bigger than it needs to be and spending a lot more money than you need to. Now, if you do need to size to a specific air change rate, you can do that, but you should understand that you're going to end up most likely oversizing your cooling system and then having reheat in a much larger, more complicated air handler to get the exact conditions you want. So it can be done, but I would just caution people about just blindly specifying an air change rate. If you're really trying to dry a room out and condition it, air condition it, to a set point of somewhere below 80, 85 degrees, just flat air change rates aren't always the way to go. So if you do need to go that route, be prepared to have extensive discussions with the HVAC engineer you're working with. The other operational mode that I mentioned was cleanup mode. And that's typically when you're not in production and you just want to purge the room. You're hosing it down, you're washing it down, you're generating a lot of moisture. Sometimes the room might be fogging if it's cool in the room. You just want to purge. So usually what will happen is that air handler will go to 100% outside air from outside and it'll speed up and push as much air through that room as possible just to get rid of the moisture. The temperature in the room might float. You won't be trying to maintain an exact temperature or humidity in the room. You're just trying to purge the room as fast as you can. So these units can be designed to switch back and forth between those modes fairly easily. Usually the air change rate in air conditioning is going to be somewhere in the 10 to 12 air changes per hour is typically what we see. When you go to cleanup mode, it would be 20 to 30 air changes an hour. And by that, air change an hour is how much time it takes, how many air changes of complete room air by volume you can purge out of that room in 1 hour. So 20 air changes an hour, you're changing out the air in the room 20 times in 1 hour. There are some other special situations we run into occasionally that are just kind of worth mentioning. And Tom kind of briefly mentioned this earlier. If you've got a large process space and you've got a relatively small piece of equipment in that space that has its own special environmental requirements, if you can, you're better off trying to enclose that within its own little room or its own microclimate. And maybe that would require dedicating a small air handler just to that piece of equipment versus trying to condition the whole room to that special case. Because that can also get very expensive if you have to treat a whole room based on one piece of equipment. If you've got a situation where your food process is generating a lot of dust, like you've got a spice storage room or powder bagging or something like that, don't treat your air handler as a dust collector. They're not really generally designed for that. You can do it, but you'll be changing out your filters every other day. Your maintenance folks won't like that at all. So if you do have special dust generating process elements, consider dust collection at source capture. Capture it at the source and dust collect it. That'll greatly extend the life of your air handler and the filters in the air handler, and you won't be cleaning it as often. Low temperature rooms are kind of a special situation. We've had clients who say, hey, we want to keep our room at 45, 50 degrees, and we've got condensation problems because we've got a lot of cold surface equipment in the room and high humidity. A lot of times you have to look at a desiccant air handling system. And that, a lot of our clients have had sticker shock when they see what that costs. They're not cheap. They're about twice the cost of a regular food grade air handler, in the neighborhood of $500,000 and up per unit. So, but that really is the best solution if you've got really cold rooms and high humidity in the rooms, because a normal air handler has a difficult time getting rid of all that moisture when you've got a low temperature space with high humidity. And one other thing I wanted to comment on is I'm kind of seeing a shift away from low temperature process rooms where you've got evaporators hanging in the room to a move to getting rid of the evaporators and putting large penthouses or large air handling units on the roof to replace them. And that works, but just as a word of warning, when you do that, the air handlers get really, really big. If you have a 10, 20,000 square foot processor and you're trying to keep below 50 degrees so you don't have to shut it down to clean up quite as often, you may go from 8 small evaporators hanging in the room to 4 air handlers on the roof that are $250,000 a piece and weigh 20, 30,000 pounds. So at the 50 degree mark, roughly, air handling units start to go up exponentially in size. So just something to keep in mind when you're thinking about either modifying a room or building a new room that's got that kind of low temperature requirement. Basic air handler construction. So now we're diving into another level of detail, even deeper into air handling construction. The image there is of an air handling unit and cheese plant. 3A standard, and you'll see in some of these last few slides, there'll be, I mentioned the 3A standard 612 occasionally a few times, and I've referenced the section number in blue text there, so that's what you'll know what it is. 3A section E1 defines basic equipment requirements. It needs to be cleanable, inspectable, with minimum seams. You can get food-grade air handlers designed to do that. The housings need to be industrial gauge, not commercial. The skin thickness on the outside and inside of the unit will be thicker than a commercial unit would be. And typically the inside liner of that air handler will be stainless steel and designed to shed water. So if you go in there and clean it out with chemicals, it'll all drain. For low temperature air handlers, you want thermal break construction. You don't want the inside or outside of the unit sweating if you're dealing with a low temperature condition. So the casing is designed to not have any thermal bridging between the inside and outside skin. Air handling units in food plants have lots of access doors. That's one of the reasons why the units are so large, is because every major system component in the unit has got access on the downstream and upstream sides of it to clean them. So lots of access doors. We also like to see fully welded floors in the drain pans in each section of the unit, so when you go to clean it out, the water will drain into the pitched floor and then run out drains. And you can see in the image there, there's the bottom of the unit there running horizontal is a common drain pipe. Okay. And finally, the insulation in the cabinet should be closed cell, polyiso, polyurethane, or polystyrene, not a mineral fiber, because that is porous, and if you do have a breach in the lining of the unit, you don't want water to get in there and collect and grow mold. Some of the other components in an air handler, fan systems. We're starting to see more and more fan walls, like that image with the box there. Instead of having one big fan, you'll have an array of fans, so if a fan fails, you can keep limping along on the other ones you have and not have to shut down production. So some little redundancy there. Don't put fans in with fan belts. Make them direct drive and put them on a VFD. It's easy to balance, and now you won't have fan dust or belt dust being generated inside your air handler. And also put in special duty fan motors that can be washed down. The air handlers typically need to have a heating and cooling source, and that could be coils, gas heat exchangers. Again, for gas heat exchangers, stainless steel. If they're coils, I don't recommend an all stainless steel coil, tubes and fins. Very bad heat transfer. Usually it's some combination of stainless tube and aluminum fin. Avoid copper or bronze coil components, because if there's ammonia in the unit, in the coil, you'll eat through it very quickly. And we're starting to see more and more UV lights in air handling units. They're very effective at, and this gets back to the biofilm discussion right before ours, they're very effective at keeping a cooling coil clean, because that's one of the places in a process air handler that will breed biofilms and bacteria, is a cooling coil surface. And just if you place a UV bank right downstream of that cooling coil, you can keep it remarkably clean, actually. We've had a lot of experience installing those with good success. So, in general, these food-grade units are designed to not have any hollow cavity components in them to the greatest extent possible. You may sometimes be necessary to put a little bit of conduit in the unit, but get all of that outside the unit as much as you can. And again, the unit should be, just like the building, the unit should be designed to prevent pest penetration. So. And also in general, the units are going more and more to stainless steel. There still are some elements in an air handler that aren't stainless steel, just because HVAC OEM manufacturers don't make a lot of it in stainless steel yet. It's hard to get stainless steel fans in these units. They're really pricey. Usually they're epoxy coated steel. Filters. The 3A standard 612 section D2 basically defines basic filter requirements. So I'm not going to go into a lot of detail there, because you can go there and see for yourself. But I also make sure when I specify these air handlers that they have stainless steel racks. I make sure that our specifications for the units require positive fastening of the filter banks, or the filters to the filter frame, so there's no air bypass. Usually there's two sets of filters in a food grade air handler. There's pre-filters at the upstream side, to capture the big particulate that comes back into the unit from outside or the process space. And then at the very end of the unit, there's a final filter, which is typically a 12 or 24-inch deep filter. MERV 14 minimum typically, sometimes HEPA, MERV 18 filters, to catch any remaining particulate that entered the unit, and as well as any particulate that could have been generated within the unit. So the air, that's the last element in the unit before the air leaves the unit and goes out to the process room, is that final filter. That's meant to catch anything that you don't want getting into the room. I'm not going to go into this in detail, but the standard 612 does have a list of typical MERV ratings for filters. So I talked about the air handlers a little bit. Distribution ductwork. You want to make your ductwork and air distribution components out of a corrosion-resistant material. Typically, it's 304 stainless steel, but there are some other materials out there. I've seen IMP paneling used for large ducts and things like that, but typically we see stainless. In general, as a designer, I like to keep the amount of ductwork I design and install to an absolute minimum, because the more you put in there, the more it costs, the more you have to clean. So the less you can put in, the better. And one of the ways we achieve that is by designing the ductwork for higher velocities and longer throw. We're not concerned about noise in a food plant the way HVAC designers are in a commercial facility. So you can design the ductwork a little smaller so that air is screaming when it goes through there. So the return air ductwork on an air handler, the air coming back from the process room to the air handler, is typically the dirtiest air that the duct system will see. So I like to make that the shortest section of ductwork possible. If that means making the supply section longer, that's okay. So I also use round duct whenever possible. It's easier to clean. It's most times it's more cost effective to build, and it's just from an HVAC standpoint, it's just the most efficient. So go round whenever you can, round duct. And please, don't let a contractor or designer talk you into putting spiral wound ductwork in a food processing unit, ever. I've seen a lot of that in the past, and it's a terrible harborage element in a system. Another thing we're starting to see a little bit more of is fabric duct in more and more facilities. So 3A standard does address fabric duct as well, so I won't go into it. Some things to note about fabric ductwork. The ductwork's a little bigger because you have to go at lower velocities. High velocities will tear and rip the fabric, so typically you don't see it at real high velocities. Nice thing about fabric duct is you can actually, when it's time to wash it, you can buy a spare, so when you pull that down, you can install a new one in and be up and running right away. So your downtime is a lot shorter if you install fabric duct. Another downside to it, though, is you got to have more of it in your process space, because you don't have long throws like you do with stainless steel ducts, so you've got to install more duct in the room. One other nice thing about fabric duct is you can get it in colors. Normally you see it in white in a process room because it's easy to see the dirt accumulation on it. You know it's time to clean it. But if you have a special purpose space where you give tours through it or something like that, and you want a colored duct, you can have one. And it's also a lot cheaper than stainless. Stainless steel welded duct is very pricey. That covers what I had.
So the topic that I am talking about today is something that I see pretty often out in the industry, is a lack of understanding of elastomer compatibility. Here's my basis on some of that. So within my group at Ecolab, there are teams that receive phone calls from all of our customers, account managers, field those calls and come back and tell us what kind of problems the customers are having. And so they're getting in the neighborhood of around 10,000 calls and questions and problems a year. So that's where I'm basing some of this, because when we looked at what those 10,000 calls really were composed of, one of the top 5 was compatibility. Because I work for a chemical company, they're saying there's something in a mismatch here. The chemical or something else is not compatible. So it really got to me that we don't really understand some of the basics around compatibility. It's not that difficult. once I break it down. Hopefully you'll agree with me, but let's get into it. I am going to start from a little bit of a higher level, just give you an idea of what is an elastomer, some of the details around that. So what am I talking about? Because there's a lot of different polymers and a lot of different things that we can talk about when we talk about compatibility. So I'm going to give you some brackets around that. I will talk regulations and standards, not as much as an FDA or USDA or somebody like that, but I do want to give you some references so you can kind of look some of this stuff up. If you like that kind of bedtime reading material is what I consider it, but it's a good way to understand some of the current thinking on some of these ideas out there. So I will give you some of those standards. Then really wanted to spend some time talking about how do I figure out what kind of elastomer is really going to be compatible, and what do I even mean about compatible? What does that really truly mean? Because as you'll find out, compatible doesn't mean it's going to last forever. Especially in this category, that is rarely what that means, is an elastomer is going to last until you're done using it, 30, 40 years down the road. That's not going to happen most of the time. And how do we look at that? How do we determine what kind of rule sets are out there? Because some of the compatibility stuff, you'll see that there's some variations out there. Apples and oranges comparisons are happening all the time. And when I look at what people are doing and how they're trying to evaluate compatibility, I'll try to point out some of those things to watch out for when you're trying to select for yourself. And then, of course, I got to give you some examples. It wouldn't be fun without a few pictures in there. This is what happens when it goes wrong. All right, basically an elastomer is pretty much, it's like a polymer or something that is a repeating chemical chain, some sort of chemical structure that we can repeat over and over again to be able to form a lattice type structure. But what makes it a little bit different is when we cross-link these chains together, we're going to keep them a little bit loose, a little bit elastic. We don't want to lock it in. If you start to lock in a polymer, anybody know what the name of something that I would lock in would be? Audience participation, come on. Like a plastic, a thermoplastic, a thermoset plastic, or something like that. So you're starting to see the slight differences between something that I purposely keep a little bit loose when I put it together and something that I lock in a little bit more strong. So it is a subset of these polymers, some sort of chemical, carbon, organic type chain that I link over and over again to produce a material. What else are elastomers called? This is what, if you're looking around the regulations and things like that, you might not see elastomer or even the term used, but if you're out in the industry, you'll see it. But it's also rubber-like material, because one of the original elastomers was rubber. And I even have a little bit of a breakdown for that for you. But because of these terminology differences, I would introduce a CAS number, a numbering system that uniquely identifies a lot of different materials out there. So as working with a lot of chemists, I'm a microbiologist, so just fair warning, but I listen to chemists all day. So I do get to hear about the concepts like this, like the CAS number that uniquely identifies something, because as I'll show you, elastomers can actually be called a lot of different things. That's one of the things that I do when I first go into a plant, is I'm listening for terminology that those plants are using and trying to link that to other terminology or synonyms for what they're calling things. Elastomers are notorious for that. So I got a nice chart showing you all the different things people can call elastomers, even though they're the same thing. I thought it was important to go through the supply chain. This is where that initial confusion comes in. So I wanted to kind of lay it out. What goes into getting you an elastomer? First off, you're going to have somebody like a DuPont, or there's a few others, Solvay out there, that's going to make a basic gum rubber. That's big, usually a big block of rubber of some type of elastomeric material, and then they're going to process that even more. So it's a base material. Think of that as like your flour or something like that. If you're making cakes or anything in confections, I worked in confections for a little while, we brought in these base materials. That's the gum rubber. Now, not all flour is the same, just like not all gum rubber is the same. It is formulated different ways to have different properties, but what's going to happen next is you use this rubber compounder who really does the mixture to make it have those unique properties. So they have an actual recipe. They're going to take that basic gum rubber, mix it in with all these different things to create these unique properties, and that's why we have so many different elastomers out there. Then after you get a certain type of elastomer, they'll usually hand that off, or sometimes these are together where you have a parts manufacturer. What am I going to turn that into? Am I going to make some O-rings, some sort of gasket, or some type of seals? A lot of different parts manufacturers out there. Sometimes they're integrated, sometimes they're not. Then what happens in the supply chain is you're going to make too many of one item to be able to sell it efficiently. So you got to go through a distributor in the supply chain. So that distributor brings in a lot of different types of O-rings. You know, if you're making Viton O-rings, you might buy from one company that's a parts manufacturer versus a different company if it's an EPDM or something like that. But the distributor pulls them all together. And then you even have another potential part of the supply chain, which is the equipment manufacturer, who then goes generally to the distributor and say, I need so many of these different types of elastomers. Why am I really pointing this out, though, is because you need to understand who knows what about the elastomers when we start to talk about, is this compatible or not? So if you look through here, would it surprise you if I hear people going back to a DuPont or a Solvay and asking the gum rubber manufacturer whether or not this is compatible with chemistry or something like that? What do you think of the chances of them actually telling you an accurate, because it's been mixed through a recipe, it's been, turned into a certain kind of part? All those things, all those processes change that. Will they give you some data? Yeah, they have a data sheet. The gum rubber manufacturer tests their material, so they have a test data sheet, but it may be nothing like what you're actually experiencing or what I would expect you to experience if we really looked at compatibility. That's more that rubber compounder or maybe the part manufacturer that you gotta understand. What kind of specifications, what kind of recipe is in there? And here is where we get that, why is it so confusing? Why can't we just make this so simple and literally just call everything the same? Because some people use common names. Some people find that common name a little difficult to pronounce. Like me, I don't pronounce a lot of chemical names correctly. Being a microbiologist again, I'm pretty good in Latin micro names, but these chemical names are a little difficult. So people will refer over to their trade name, like neoprene, or like I said, Viton. Those are names that actually may not be Viton, because Viton has two types, type 1, type 2. So which one are you talking about? You could actually be talking about a type 2 fluorocarbon, FMC, and it's actually a type 1, but you called it Viton, so that if I knew exactly what Viton was, I would get a little confused if you were talking to me about compatibility, because I would have thought by the name you were talking about type 1, and I get, a lot of confusion there. And the other thing, something like this chart brings up on understanding what you're talking about. People have seen these charts, or you can pull these charts just like I did off the internet, and understand there's a temperature range. Well, what does that temperature range mean? That temperature range means as a compounder, I can expect to create recipes that are within this range. Does not mean what some people interpret this as nitrile is good from -65 to 250 Fahrenheit. That is not at all what that means. It means I could make something, a recipe with that base gum rubber into things in that range. So that misinterpretation or misunderstanding leads to some failures, some early failures. So you really got to understand the same thing with the hardness ranges. So how difficult it is for me to squish and compress. Those are generally ranges. That means I can start with that base material and produce something within that general range. It's almost never good for the entire range. That's not what these things usually mean. So going on a little bit is the elastomers themselves. Just what is it? I really saw this and I want to try it, but I haven't gotten the courage to do this yet. But it's a home recipe for making your own rubber. But I thought that was really great to understand how simple and how basic this is you collect, in this example, you're collecting the rubber from a rubber tree, that extract that comes off the tree. Think maple syrup. We're close enough to Canada, right? You can understand how maple syrup might be collected. Then you compound it with, in this case, they used a morning glory extract. So simple initiator, it started that cross-linking. They press it and then they dry it, and you have sheets of basic rubber. So relatively simple. All you're doing is trying to create those repeating units over and over again to produce this material that's flexible, that's loosely linked together. Here's the regulation parts. Learning a little bit about, most of the regulations refer to with the food contact substances. There's a lot of rules around what we put together and what we put in contact with these food contact substances. I tried to go into detail, trying to read each different way that you can produce this, but I came to the realization that I'm just going to have to refer to a whole section. So 21 CFR 170 to 199 talks about a lot of these different materials, because sometimes we're combining materials. I'll show you, or I'll talk about an example where rubber and plastic get combined. So the smartest thing to do is just to start to become really familiar with this whole section. It's a section that, as a chemical company, we kind of live and die by, because a lot of the stuff that I do out in the industry has applicability in this section. I did break down a little bit more, where if you're looking for CGMPs, the section 117.40 really talks about the equipment and utensils. So if you're just looking about how do you put together and how you would use that, or the 177.2600 is a little bit more well known. A lot of people you'll see that are trying to sell you elastomers will refer to this, because it gives you a list of acceptable materials, and it gives you some extraction testing that might need to be done to qualify it. But I did find another reference that was talking about there are other ways outside of the 170 to 199 that you can have a food contact notification. There's a lot of different paths for people coming up with some very unique elastomers to get it approved for food contact. Luckily, I have a regulatory team that backs me up, and when I get some of those phone calls or they get directed my way, we'll help you sort it out. But really what I wanted to point out with this slide is it's relatively complicated. So if you don't fully understand it, you're not alone. Reach out for help. There's people who will help you, guide you through some of that. Some of the other things are USP. I tossed in here USP class 6 here, because what happens is that is not an actual regulatory, but if a regulatory reference refers to something like this standard, then it becomes a regulatory guide. And then also the European codes here for food contact and GMP compliance. I toss those up there. If you're really into this, make sure you become familiar, read it, and then you'll be able to ask a little bit of questions when you start to get into this subject. What about standards? So those are some of the regulatory guidance standards. There's a lot of standards that are produced out there. So again, it's not so easy to understand elastomer compatibility when you're looking at a fair number of standards here. Got to reference the 3A standards on gaskets. and seals, pretty much. It gives you different classes. It's nice to refer to that and see the different testing methods and start to understand some of the terminology that you're going to encounter when we get over into trying to figure out which one is going to be right for you. There's different characteristics. If you don't understand the method on how we're testing it, ASTM, there's a lot of test methods out there that go into detail. How do you test it so that you can compare from one to another? Also, some storage requirements out there. There's ISO storage requirements, SAE, different, because elastomers, like I mentioned before, they do not last forever. Then when you use an elastomer, usually you've got stockpiles somewhere, right? You're changing out your gaskets. How long do those stockpiles sit? How often do you change those stockpiles out? Because they have a shelf life. Most of them do, especially if you don't store them in the greatest conditions. I've been in many maintenance departments where I'm trying to find a gasket and I grab gasket after gasket and it's like, what is wrong with all of these? It's poor storage. It was right next to a engine or boiler room and it just was not stored properly. They don't all last that long. Food grade and antimicrobial gave you a few more ASTM references there, and then the United States Pharmacopedia, class 4, establishes more medical grade, but I'm just giving you references because I find I can borrow what people do outside of food, and once I understand kind of what their standards are, how much of that applies to me. So if you really want to deep dive, that's what I kind of did here, give you a list where you can read for days and days on elastomer compatibility. And then finally, NSF. Again, this is me reaching into another industry that's typically a little bit more for commercial and restaurant type of equipment, is the ANSI 51 standard out there. But does it not apply? I can't tell you. Some of the things they put in there don't apply. So if you're just trying to understand what to look at and how to pick the best elastomer, get the right compatibility, it's another good reference material. Now let's get into choosing an elastomer. A lot of people understand this first box, the properties. Especially if you're an engineer, you're trying to design a certain piece of equipment that has these certain characteristics, you're gonna know elastomers have to have a certain durability, flexibility, you got a temperature range, and it's gotta be configured in the right component, the right size. Maybe it's a certain O-ring shape or some other type of shape, reinforced, not reinforced, things like that. That I don't see a lot of problems with. Most people understand that a 1.5 inch O-ring will not fit a one inch pipe or something like that. But what I start to get into more questions is, now that we talk about, well, how are you using that? What are your conditions? Oh, does that matter? Well, what are you making with this? Are you making dairy or are you making mustard? Because they both flow through pipes, but trust me, they will not treat your elastomers the same. It's not even going to be close. Or there's a lot of other characteristics. And then to compound that a little bit further, I try to ask about, okay, how are you going to clean this? What is your sanitizing protocol? If you do know what you're making, that's going to help me a little bit to guide you to the right compatibility conversation. But if you don't know how you're going to clean it, you haven't decided that yet, that's going to put a real challenge, because trust me, we don't usually clean it with the same, very similar property chemical than what you're making as food. You know, few exceptions, but even water. I don't clean water lines with water. So you really have to understand not just what you make, but also how you're going to clean and sanitize it. There's people to reach out to if you have any questions on how you might clean a certain product. We've got a lot of that figured out, but you need to have that kind of information when you start to look at what kind of compatibility for my elastomers. And then also, I tossed in there that storage, because that's something that I keep seeing people miss, is that storage. How long are people supposed to be storing this? How long are you expecting them to store it? What's your change out program and the conditions and how you're storing that. You can't just shove this on a shelf somewhere. Be careful with that. I did toss in here some examples of shelf life. So several, under the right conditions, could be unlimited, but then it goes from unlimited to 15 years, 5 years, 3 years, and some of these are cost related. As far as you can tell, the cheaper ones sometimes are a little bit quicker. They expire really fast. So if I have someone that has a 1 year exchange program on their gaskets and they buy enough for the next 10 years, okay, we got an incompatible thought process there. Because what you just got is you're basically just asking for me to come back in the other capacity as a microbiologist and figure out what all these counts are coming from, because those are going to degrade on the shelf where you put a new gasket or a new elastomer in place and it's already bad, or it's bad after the first wash or something like that. So got to keep that in mind as well. And then you get it complicated a little bit where you encapsulate one type of elastomer with another, or maybe you're putting a plastic in there, or I've even seen metals being combined with elastomers. So now I'm not just worried about the elastomer, but what else is it combined with? How is it combined? So those chemical resistance, I'm going to give you a few techniques, but these are some of those exceptions to the rules on figuring out if I've got something compatible. Even things like adding metal detection, right? Metal detection's very popular in certain parts of the industry. They really want their elastomers to be fully metal detectable. But one of the basic principles of making a recipe, especially the elastomers, is whenever I try to gain something, I give something up. I do that in sanitation. It's always a balance. In order to do it right, if I try to gain something, I'm trying to speed up sanitation cleaning time, then that means I have to go higher concentration. Elastomer recipes, if I want to gain a higher temperature, then I'll lose chemical resistance or something like that. So those recipes are all balanced. If I gain metal detectability, then I'm probably going to be less flexible. So it's going to be more susceptible for certain types of defects. So keep that in mind. A metal detectable EPDM gasket is not the same as a non-metal detectable EPDM gasket. They won't perform the same. Why is it important? I'm thinking this might go without saying, but I really wanted to drive this home because of where we are. We're talking about sanitary design and how much of an impact that is. So the flexibility of materials when you're putting together a food process, you're going to use it. I see them all over the place. You're going to find these flexible materials in food processing. It's very rare that you can perfectly match things up without any use of elastomers. So it's out there. They're often pretty small, relatively small little gap in a pipe. That's your elastomer on a gasket. But do they have an impact to it? Yeah, a lot of times these elastomers are food contact or near food contact, close enough that they'll have an impact if they're not managed and maintained well. Can they hold microorganisms? Absolutely. I have had many instances where I have discovered the elastomer as the source of some pretty big incidents, some real headaches that, I mean, they were going on for months, causing hundreds of thousands and millions of dollars worth of loss because of these materials. These relatively small, but can harbor bacteria, things like that, that will affect. And then just the fact of how you have to make them, that loose cross-linking structure makes these particularly susceptible to things like the compatibility concerns on chemistry or temperatures. If you go one time out of its temperature range, now how much have you reduced the life of that elastomer? Could be time to replace it right now. And so even selecting the right elastomers or swapping these out because they look close enough. By look close enough, I mean that first blue box, it fits. But if not everything else, then you got to worry about there's food safety risks, different kinds of risks in there. So a lot of misunderstanding too. I identified that as a big risk here is elastomers, what they can do, what they can't do. There's a lot of misunderstanding of even what they are sometimes. So trying to educate a little bit more on the importance of this. But what is that impact? I mean, you name it. I got about all the food safety quality concerns up here, as well as performance. As far as toxicological, can chemicals sometimes leach out of these things that you weren't intending, or maybe they're holding on to an allergen or something like that, because I know Joe's going to talk about allergens a little later. So toxicologically, this could be a concern. Microbiologically is definitely a concern. They create gaps that are huge caverns for tons and tons of microorganisms to hide in. What about physical? I mean, I try not to tell too many stories, but I remember a time troubleshooting some ice cream cones. Beautiful new machine, makes amazing ice cream cones, really fast. And before we coat them, people were noticing that there was these little discolorations, these little specks on them, right? I'm like really looking, I was thinking micro, maybe poor sanitation or something like that, but ended up getting worse and worse. The more aggressively we cleaned, the worse it got. I'm like, what is going on here? We were scrubbing all these surfaces, and then it comes that it was the elastomers were not compatible with what we were doing with sanitation, and they started sprinkling themselves on these pristine white, now peppered ice cream cones, and nobody wants that on their ice cream cone. So yeah, just that visual change when these things fall apart, you can get affecting a lot of product. Or taste-wise. Nobody wants to bite into a little piece of an elastomer because your teeth are definitely sensitive enough to pick out really small pieces. Not necessarily harmful if it's small enough, but that springy texture that just doesn't give when you bite it, you'll get a complaint on it. I've been in jobs where I've heard a lot of complaints, and people do detect little bits of gasket, and it's really hard for me to just say, can you send that back? I need that. It's like, no, they don't usually send it back. But performance-wise, you also have key issues with performance. A lot of the maintenance people or people who are in charge of these programs are pretty much on top of these fairly often, but there are bright spots as well as dark spots out in the industry as far as it can lead to equipment failure, premature equipment failure, if the elastomers are not keeping the solutions where they're supposed to be, or things like that, as well as product loss. So a little bit more on how to determine, talking through the process. So what do we look at when we're trying to figure out, is this the right part? So specifications. Really, if you are purchasing or in charge of elastomers and you don't have specifications where you've written down, these are the characteristics, these are the qualities that I need to do this job, I encourage you to take a look at this list and think of all these different ways to specify the type of elastomer. All these different properties, and how are they checking those properties? Is there an ASTM reference? Is there an ISO reference on how they check it? Or when they say flexibility, it's 0.25. What the heck does that mean? Well, we just pull it and measure how far it pulls when Scott over here pulls it. Okay, that's not very technical, but at least you're giving me a number. But the idea is you try to reference that, because so many times when we dig into some of these issues, we find people out there that are making these things running along just, this is what we do in-house. It's an in-house testing method. If you don't see it, ask about it and make sure you understand it. Same thing for most of these tests. The temperature range, the shelf life, how do you determine that? Oh, we just throw it in the warehouse and we pull it out, and if it looks good, we're good. No, there's actual testing methods out there. And then when they say FDA-like materials or things like that, little red flags that should go up. No, tell me the reference. Like, which one out of that 170 to 199, exactly what materials are you talking about? Or give me your FCN, food contact notification, or something like that. Resistance, same kind of thing. Start to talk to them about how are they testing their resistance. I'll go into a little bit more detail on chemical just because I can. And my R&D team helps me out a little bit there, but honestly, you really want to ask them about how do they test for some of these other conditions that might be present if you're doing UV or something like that in the system. So check on that. Because it looks kind of like this. It can look something like this. These guides that are out there that manufacturers put together, I really like the wheel one. It felt like I was playing Wheel of Fortune on guessing which was the compatible elastomer for me. But honestly, they come in all different. Sometimes people will make it look very technical, like the one on the far right there, and sometimes they try to make it fun, like the one on the left or somewhere in between, where 2 green checks versus 1 green check. What does that mean? What is 2 green checks comparatively? Is that 25% more? 50%? What does it actually mean? So it can be difficult to figure that out. But there is something that's very common out there is these compatibility guides, the chemical compatibility guides. And there's a lot of different versions of them out there. But believe it or not, a lot of the material comes from very similar places. Most of these are not producing these chemical compatibility guides on their own. They're not doing all the testing. They're pulling references for it. With the exception of certain chemical companies out there where we've tried to do a lot of testing to make sure it's fitting, the chemical that is released is going to be compatible with all the things that we would expect to experience in that environment, the different types of elastomers and those types of processing. You are not supposed to read that fine print. I wanted to make it as small font as possible, but you will find that on many of these guides is there's fine print saying this is to the best of our knowledge. If your results vary, tough luck. You know, that's kind of how that goes. But there aren't really guarantees behind most of this compatibility information that's out there. They're just saying, we've done some research for you, here you go. And I didn't mean that to segue into this particular guide because I actually like this one quite a bit because they break out, give you a lot of different types of information and things like that. So just an example. I'm going through a few of these because I put a lot of reference material in here for you just because I wasn't sure what all you'd want. But when do you test? So if you can't find a perfectly compatible elastomeric material for you, you may need to initiate some type of testing. A lot of times there's people that will do some of this testing for you, like your chemical provider or maybe the supplier of the parts. You ask something specific, try to initiate a trial. Even putting something in, just the solution or just the conditions that you intend to impose upon it is some type of test that starts to get you the idea of whether or not this is going to survive. Certain things you're looking for, flats, damage, some sort of physical change of it. Any condition, it could get heavier, could get lighter, could get sticky, could get greasy. You know, those are things that you're looking for. Give you a quick example. This is something that we do over with our new chemistries. We mix up different chemistries to see the impact. This is an example of a 28-day soak test where we're doing full concentration for 28 days, higher temperatures to try to maximize the potential of us to catch any compatibility differences there. This is silicone rubber and a lot of different formulas that we were trying to push the envelope here. Obviously, they didn't all work. So you got some major changes. Most of these you see they picked up quite a bit of mass, so they became much more spongy, and some of them cracked. So I already mentioned a lot of these things that you're looking for when you're checking compatibility. Those permanent distortions. One of the great things about elastomers is they return to their original shape. That's what you want them to do. If they aren't, then something permanently has changed that is not compatible. Just break down what role can you play, because we each have different roles out there. If you're equipment manufacturer or facility in construction, if you're in there, what should you should understand, start to seek and learn about sanitation conditions. What kind of conditions? Not just what are you making, but how are you cleaning it? And if you don't use specifications, start using specifications for the elastomers, so that when somebody in purchasing, let's say, decides to go with some, well, just about the same kind of elastomer, you've got that specification that will say, when you say just about the same, is it the same? Chemical providers, we're continuing to build testing database, but we need input from people who use the chemicals out there. What are you seeing? What do you need tested? Different conditions, because try to predict it all, but honestly, the feedback needs to come from the food manufacturers. So if you're talking to a chemical provider, let us know those test conditions. What are more common elastomers? If you're a CPG or food and beverage, ongoing performance evaluation. Note the condition. When you go out and replace a gasket, do they note what condition the gaskets were in when they replaced them? That's a simple one that I've seen missed so often. I was like, you have this gasket replacement program, but you're not telling me what condition they were in. And I know they weren't all good. I've done a lot of gasket replacements in my time. And conducting sanitary design reviews and selection guides. Here's my last slide about pictures. I just wanted to give you an example of what you're looking for visually. So if it expands, it's not going to fit. It could cause some issues. Cracking is obvious. Chemicals on the right will give you like that oily substance or that compression set. This is a really good one because a lot of people can relate. You close off a faucet. After you close off the faucet enough, it starts to leak. That's because of compression set. It permanently deformed it. Or that gasket that I saw that was clamped down, someone was using a tool to clamp. You're going to get installation damage. You're going to get things pinched off and little pieces are missing. Or overall, time will wear it down so the elastomer will start to disappear. So hopefully I gave you a few things to think about and to look for.